Astronomy Seminars. It's my pleasure to introduce Peter Behroozi. Um, Peter Peter's bio is he went to Stanford, where he worked with Risa Wexler was his advisor. Um, and then he did postdocs at Stanford Space Telescope, Berkeley, where he was a Hubble Fellow. And since 2017, he's been an assistant prof at University of Arizona. As Peter will describe, he's very well known for his work, sort of blending the observational world, in particular reconstructing the star formation history of the universe, and then matching that via n-body simulations and other techniques like abundance matching to present a picture of how galaxies are connected to their dark matter halos. Peter said he's happy to have questions during the talk, so raise your hand and I will call on you if you have a question, but if for some reason I've ignored you for too long, then I would just go and interrupt. All right, so today he's going to tell us about decoding galaxy formation with the universe machine, all one word. Take it away.
So thanks, Mike. And it's a great pleasure to be giving this presentation, even if virtually. It'd be great to visit the University of Waterloo at some point when all of this has passed. So as Mike said, I'm very happy to take questions during the talk, and I also have questions for you to make sure you're following along. I like to do some interactive questions during my talks, just to make sure that everyone is following along and getting what I'm saying. So the topic of the talk today is galaxy formation. And before I get to the science, I thought it's worth pointing out that for astronomers, a very important part of their job is not just teaching, not just research, but also outreach. So I wanted to say a word or two about the outreach that I do. So I work with veterans. I work with the Warrior Scholar Project, which is a transition program for veterans moving from the military to college. And many people don't realize this unless they've served, but veterans have sort of very many intersecting underserved backgrounds, including ethnic and racial minorities, coming from places of lower socioeconomic status, first-generation college students, many have mental and physical disabilities. And so you have all of these different sort of challenges coming together. And even though our government pays for veterans to go to college, they drop out at much higher rates than the general population. And so the program that I help run is a science-based program to help veterans see what it's like to be in college, to have a community of other people they can talk to if they're the first generation in their family and so they don't have outside advice, as well as to do many research projects and talk to real scientists to understand what is it like to have a career in science. And so besides being a lot of fun, it's also very effective. People in the program pass college and succeed at much, much higher rates than veterans overall. So if you have any questions about that, I'm happy to answer those as well as long as any science questions that come up. Great. So before I talk about galaxy formation, it's usually a nice thing to ask, well, why even bother studying galaxies? So if you already study galaxies, then you know why. But if you don't study galaxies, why should you care? So if you study large-scale things like cosmology, here's an image generated from the Planck collaboration results about what's in the universe. So you have dark energy, you have dark matter, you have baryons. Galaxies actually don't even show up because they're too tiny in this whole scheme of things to actually matter that much. So why bother? I think of galaxies almost like streetlights. So if you look at streetlights, they're not a big sort of portion of the mass of the Earth, but they can tell you some really important things. For instance, where people cluster. And just like streetlights tell you where people cluster, galaxies are the streetlights of the universe. So they tell you where baryons and dark matter cluster. And you can also use them as tracers to understand how dark energy has impacted the evolution of the universe, or the expansion of the universe. And current experiments, for instance, to detect the influence of dark energy and to measure how that has changed over time are limited not by statistics, but more by systematics. What is the connection between galaxies and the underlying matter fields? And so it becomes important to study galaxies to understand those systematics, to really get all the power that you can out of these very expensive experiments. Zooming into smaller scales, if you study something within a galaxy, for instance, there are lots of very interesting physical processes there. So star formation, turbulence, gamma ray bursts, planet formation, gravitational waves, dust formation, supernovae, cosmic rays, and so on. And if you understand galaxy formation, then you understand the context in which all these different interesting physical processes occur. So just to give an example, let's say you find a new type of supernova. And you also find that that type of supernova, the behavior is different depending on which host galaxy or which type of host galaxy it's in. So for instance, let's say it shows up more often per unit stellar mass in more massive galaxies. And so that immediately tells you, if you know something about the history of the formation of that galaxy, that tells you that that supernova might be linked to the metallicity of the stars that is formed, or the time delay since those stars formed before the supernova goes off. If you have those pieces of information, as in time delay as well as metallicity, that immediately gives you a hint about what is the progenitor star for that supernova. So you didn't have to do any extra effort except just to look at the host galaxy of that supernova, and that immediately tells you what kind of star might have given birth to that supernova. So there's a lot of information encoded in the galaxy, and so then it's useful to understand how do galaxies form. Great. Okay, so then the next question is, well, why is it hard to study galaxies? And you'll notice that this slide looks exactly like the previous one, and that's because galaxy formation is driven by many interesting physical processes, and to understand galaxy formation truly requires understanding how all these different physical processes fit together. And as any observer or theorist will tell you, we're a long ways from doing that. Okay, so then I want to tell you about some progress that we've made in this direction, understanding how galaxies form. So I want to sort of go over the tools that we have to study galaxy formation. So there are two main ones that everyone knows about, and then a third one that I've helped develop that I'll talk about mostly during this talk. Okay, so the two ways that everyone knows about, first one is observations. So we can, of course, see galaxies at many different redshifts, many different points in the history of the universe. You can see galaxies nearby with the Hubble Space Telescope, and soon, hopefully, with James Webb. We can see galaxies in the very far past because, of course, it takes time for the light to travel to us. So we can see galaxies almost at the Big Bang. We can see galaxies nearby. But these are only single snapshots. So we don't have movies of how galaxies evolved because it takes hundreds of millions of years for a galaxy to appreciably evolve that we can see. And so we can look at a galaxy like this today, but just from that snapshot that we have no idea about the formation history of that galaxy, or we have sort of crude ways of getting at the formation history, but not great. And we have no way of saying, for instance, whether this galaxy, which galaxy this looked like at redshift 8, for instance, or even how this galaxy grew, whether it grew rapidly and then slowly and then rapidly, or then slowly for a long time and then rapidly. So in other words, we can see what it looks like today, but we have no way of connecting this to the past with observations alone, so we can trace how did that galaxy grow over time. Okay, so on the opposite side, we have simulations. So we have ways of, say, putting in the physics that we know that affects galaxy formation. We can put that into a giant computer and press go, and we can get movies of galaxy formation, and they're fantastic. If you look, you can find many videos on YouTube about galaxy formation simulations, and they look great. The issue is that the physics that come in at small scales end up resulting in very large changes across the rest of the galaxy. So here's an example of sort of two different ways of putting in feedback from the stars. So the stars, of course, explode. They exert forces on the gas around them. And depending on the mechanism that you use, you can get very different movies out from relatively similar assumptions about the physics that go in. And we just don't have the resolution with simulations to really get at what's happening with star formation, putting in all the physics we know, because let's just take an example. If a supernova goes off in a galaxy, it will inject energy at the scale of the star. So that's a few light seconds. that energy will propagate across the entire galaxy out to sort of the edges of its dark matter halo. So that's not light seconds, but that is 1,000,000 light years, right? So if you divide 1,000,000 light years, that distance out to which energy propagates by a light second, that's 10 to the 12. And so in 3 dimensions, you have 10 to the 36 sort of resolution elements that you need to resolve. Or if you need to resolve the time scale for that, then that's another factor of 10 to the 12. So 10 to the 48 operations you would need to actually evolve a single galaxy at full resolution. And so no one has that, and no one will have that for potentially hundreds of years. And so you always have to put in guesses, and those guesses turn out to matter because small scales, things that happen on small scales, propagate out to big scales. Okay, so those are the 2 things that we had, observations and simulations, and I've been helping to develop a third approach, which sort of combines the best aspects of both. So in other words, empirical modeling is a third approach where you can actually then generate movies for real galaxies. That is, you can stitch together observations of real galaxies. So the universe takes care of all the simulation at high resolution for you. And it's just then a way of connecting galaxies together across time to understand how do they evolve. Okay, so I'll get into a little bit about how this works. But I just want to connect in your heads the empirical modeling that we're doing with galaxies to an empirical model that you already know and are already familiar with. Okay, so what's that? You already know an empirical model that is for cosmology. So for instance, we have a dark energy density in cosmology. We have a dark matter density in cosmology. To date, we have no idea what either of these things are. We don't know what dark energy is. We don't know what dark matter is. All that we know is that there is some kind of matter in the universe. It doesn't interact with light. We know that there's some kind of energy driving the accelerated expansion of the universe. So we can parameterize how these 2 things affect the expansion of the universe and all the observables that we might see. And then we can run experiments. So we can make observations and we can combine observations to constrain how much dark energy, how much dark matter we have in the universe, right? And the nice thing about this is that if you have different types of observations with different degeneracies, like supernovae, cosmic microwave background measurements, baryonic acoustic oscillation measurements, then you can get a much tighter constraint on the amount of dark energy and dark matter. Even though you don't necessarily know what they are, you can at least get a constraint on how much of them there are in the universe by combining different observations. And the same thing is true of any other empirical model that you develop. So in other words, if you have many different observations that you're combining with different degeneracies, it doesn't matter that you're talking about dark energy and dark matter. Any aspect of galaxy formation or planet formation or any other empirical model that you develop can benefit by self-consistently combining many different pieces of information. And so that's really what has made my approach really powerful for understanding galaxy formation, is that I can combine all the millions of observations of galaxies that people have done over the past several decades into one self-consistent whole that really constrains how must galaxies form in dark matter halos. Okay, great. So let's talk about how we build this up for galaxies. So I'm going to go back to your graduate classes in astronomy or undergraduate classes in astronomy and just talk about how do galaxies form. So galaxies form in dark matter halos. So you have a dark matter halo that has gas in it. So dark matter collapses into a halo. It brings along gas. That gas cools radiatively into a disk, and you form stars in the middle of that disk. So this is sort of the basic picture that we've had for the last 30 or 40 years. So then I want to talk about dark matter. So dark matter, we have a much better idea of how to make a simulation, a realistic simulation with dark matter. Because dark matter doesn't interact with light or anything very strongly, just mostly interacts via gravity. And gravity is easy to simulate because it doesn't have the same nasty behavior of things on small scales propagating out to very large scales. So in other words, a small change on a small scale is a small change on a large scale in terms of the gravitational potential. So that means we can put in the initial conditions of the universe as, say, measured by looking at the cosmic microwave background as well as a few other experiments. And that gives you the power spectrum, so the sort of the density fluctuations across the universe. You can put that into a computer, you can turn on gravity, and you can get an answer that agrees to within 1% of other people who do the same thing. And that's really nice because it means on sort of large scales, on the scales of dark matter halos, we sort of know how the gravitational potential wells of the universe grow and evolve. And so here's a movie of that. It might look a little bit jerky to you, so I'll try to describe what's happening here. This is showing a simulation of a dark matter halo growing. It's going to be a cluster, so a very large gravitational potential well. The main thing is that in lambda CDM, so lambda plus cold dark matter, you have small things to start with. Those small things grow by accreting matter from their surroundings and merging with other small things to get larger and larger over time. So I'll just wait for this to play so you can see all these small things then converging into this larger and larger object over time. And we call this sort of large object, this virialized region of dark matter, a halo. So that just means that this region, this sort of green region here where everything is very dense, that's where the dark matter is virialized, equal sort of potential and kinetic energies, and we call that region a halo. Okay, great. So what can we learn from these simulations? We can learn lots of things. So we can take measurements, for example, for a given cosmology. How many halos do we get as a function of how big they are? That's the mass of the halo, as well as the redshift. So we can measure sort of the growth of structure over time. We can also trace individual halos back in time and see how big they were at earlier times in the universe. So for a given mass today, we can trace them back and see how big they were on average, or what was the spread in sizes or masses for the halos at earlier and earlier times. So we really have a way of connecting objects through time with dark matter simulations. Great. So how do we build then a model for how galaxies form? How does this help us? Okay. So the concept is we have something that we want to understand. For example, how do galaxies assemble their mass? That is, how do they assemble their stars? And we have things from the dark matter simulation that we can measure with time. So things like the halo mass, or the mass of the halo, as well as the time. So if we can relate somehow the stellar mass of the galaxy to properties of its host halo, that is, how do galaxies grow in halos over time, then we can learn something about the physics of galaxy formation. Okay, so let me say a little bit about why is this a useful construct? That is, why is it useful to know how the stellar mass of a galaxy depends on its host halo mass and the cosmic time? So I'll show this picture then of what that actually looks like. What I'm showing here in this graph is sort of a galaxy formation efficiency. That is the ratio of the stellar mass of a galaxy to its host halo mass as a function of the halo mass, and for different scales here. So things like dwarfs are on this side, Milky Way would be here, you have groups of galaxies and clusters of galaxies over here. When a halo first forms, that is when gravity pulls in dark matter into a virialized region, it also pulls along gas, and it pulls along gas at approximately the cosmic baryon fraction. So that's about 16%. So if all of that gas were to form stars, then you would see a ratio of stellar mass to halo mass that would just be a flat line like this. So independent of the mass of the host halo, that is sort of the gravitational potential well depth, you would just see this flat line where all the baryons turned into stars. But in real life, in the real universe, we don't see that. We see a sort of shape like this that rises from low halo masses to sort of Milky Way-ish masses, and then falls off towards larger masses. And the fact that this line, or this curve really doesn't look like a flat line like this, tells you that there's something preventing all these baryons from turning into stars. And by looking at the shape of this line, that can tell you something about the physics of what's happening. So at the sort of low mass end here, you have feedback from stars. So stars become supernovae, so they explode. Also stellar winds, the cosmic rays, basically different ways of, as you form stars, dumping energy into the gas around and then blowing it out of the region that can form stars. And for more massive things over here, the gravitational potential well depth is so deep that none of the stellar feedback mechanisms work so efficiently anymore. And so you have to appeal to other things. So for instance, long cooling times plus perhaps a supermassive black hole at the centers of galaxies that's helping to heat the gas and prevent it from forming stars. So this relationship between the mass of the galaxy and the mass of the halo, or the ratio of this stellar mass to halo mass, is telling you a lot about the physics of star formation in galaxies. So to measure the shape, that is, to measure how stellar mass depends on halo mass and cosmic time, really tells you a lot about how galaxies must be forming. Okay. And then how does this work in practice? I just want to say this just in a slightly different way, and maybe that will make it clear. We can, of course, see galaxies at many different points in time, right? So if we look further and further back in the history of the universe, we can see galaxies as they were at different times. And so if we have a dark matter halo in a simulation, we can, of course, trace exactly how it evolves with time. And so if we have a way of matching observed galaxies to halos in simulations, like if we say for this halo, this galaxy was likely living in a halo that looks like this. At this redshift, this galaxy is likely living in a halo that looks like this. This galaxy is likely living in a halo that looks like this. Then we have a way of using the sort of growth rate of halos that we know from simulations to get a constraint on the growth rate of galaxies in observations, right? So the better the link that we can make between observed galaxies and halos at different redshifts, then we can use the fact that we know the redshift evolution of halos in simulations to get the redshift evolution of real galaxies in the real universe, right? And the stronger or the tighter the connection that we can make between real galaxies and halos, then the more that we can learn about galaxy evolution. Okay. Great, so this process lets us build movies of what real galaxies are doing. And as I said, it really matters that there's a tight connection between galaxies and halos, because if it's no connection at all between galaxies and halos, then we're not learning very much information from doing this matching process. So it's fortunate that stellar mass is tightly correlated with halo mass. And so you can measure this in many different ways at sort of the present day at redshift 0. So for massive clusters, you can use X-ray mass measurements to get at the mass of the halo. You can also use weak lensing and clustering to get at sort of intermediate mass ranges. You can use satellite kinematics and also some recent weak lensing measurements. Mike has been responsible for some of those at lower masses here and sort of here. And that means at redshift 0, you can get really a wide range of measurements of halo masses, and you find that there's sort of a very tight scatter of about 0.2 dex in the stellar mass at fixed halo mass across several orders of magnitude, at least 3, if not 4 orders of magnitude in halo mass, right? So that actually means that you can connect galaxies to halos and learn something useful from that connection. Okay, so there are tons of ways of making this measurement at redshift 0, and they all become much, much harder as you go to higher redshifts. So by redshift 1, you can still do some of these measurements, but by redshift 2 and 3, it becomes super, super hard. So how do you actually get the full history of galaxies in halos across the age of the universe? Okay, so no one knows ahead of time, for instance, what is the galaxy formation efficiency that we're interested in at higher redshifts. So how do we actually get a constraint on this? Okay. So there's something really easy that we can do, and that's just called guess and check, right? So in this space that we want to learn about galaxy formation efficiency, we can make a guess for what is the ratio of stellar mass to halo mass as a function of halo mass. And let's say it looks like this. And if we're, say, thinking about redshift 1, we can go to our dark matter simulation and then say how many halos are there of a given mass in that dark matter simulation. And we can populate them with galaxies according to our guess over here. So for instance, let's say we guess that a 10 to the 14 solar mass halo has a 10 to the 11 solar mass galaxy. We go to our dark matter simulation. We say that there are sort of this many halos of mass 10 to the 14. And then we can make a prediction. If this were the correct galaxy formation efficiency, how many galaxies should we actually observe? And so that's sort of indicated by this red line here. And then we can just make a comparison. Is our guess anywhere close to actually the number density of galaxies that people observe in the real universe? If the answer is no, which it probably is to start with, then we can just play around with our guess over here and change it a little bit, right? So if we increase the efficiency of galaxy formation, that corresponds to an increase in the stellar mass of all galaxies. So that wasn't quite the right thing to do, but if we tilt the shape a little bit, then we can get something that matches better like this, right? So it's a very easy thing to do. We just guess and check and guess and check. And this guessing and checking uses no assumptions about what's doing the feedback here or the feedback here. It's just a very simple empirical prescription to say that there is some underlying galaxy formation efficiency. We can guess what it is, and we can compare that to observations to get a constraint on what galaxies are actually doing without making assumptions about what is driving that feedback. Okay. So the fancy name for guess and check is MCMC, of course. And so you can repeat this process over any redshift where you have measurements of galaxies, right? And so it's very easy to measure number densities of galaxies, relatively speaking, at a wide range of redshifts if you don't have to measure their halo masses. So you can just measure number densities. How many galaxies are there of a given mass at this sort of age of the universe? And you can immediately then get out constraints on the galaxy formation efficiency that are independent of assumptions about feedback, just from this approach of guessing what this must look like to match the actual observations over here. And of course, you can fold in all the observational uncertainties, both statistical and systematic, in making these constraints on this side. And that was the subject of a paper that I wrote in 2013.
There's two questions, if we can
Great.
interrupt you. I think Neil was first.
Oh, yeah, like, well, so my question was actually for it was for a slide, I guess, several slides ago.
Sure.
So you mentioned, that so you mentioned that there's a strong correlation between stellar mass and halo mass empirically. Yeah. So does that statement mean that the scatter between the two is small?
That's correct. So this plot is not really showing you the scatter so much. It's just showing the many different ways of measuring the stellar mass to halo mass relationship. And many of these ways will also give you a handle on the scatter. So for instance, HOD methods, clustering methods, also X-ray methods, and lensing methods will give you some control on what's the scatter and stellar mass to fixed halo mass.
So
and
how does lensing do that, for example? I mean, so lensing is just measuring like a stacked, like average profile, right? So the scatter, yeah, I think, drops out.
Yeah,
right?
so you're sensitive because you know the number density of your targets, right? So if you take the lensing signal around all galaxies above a certain cumulative number density or a certain, say, threshold stellar mass, you know what the number density of objects is. And if you have absolutely no scatter between galaxy mass and halo mass, then all of those objects will live in the most massive halos possible, presumably. And so then you'll have a higher lensing signal than if you have scatter between stellar mass and halo mass, where some of those galaxies then are living in slightly lower mass halos.
So you're sort of combining lensing with abundance matching in some sense.
Yes, yeah, so a pure lensing signal, if you don't include the number density constraints, will not necessarily give you a handle on the scatter, but if you use both constraints simultaneously, then you do get a handle on the scatter.
Okay, so you're modeling the scatter somehow, like a Gaussian or something, and then you constrain what that scatter is, you're saying, via combined abundance measurements and also then like stacked measurements.
Right.
Is that the idea?
Yeah.
Okay.
And that's the same for clustering. So with clustering also, you can't get a handle on the scatter unless you really combine it with the number density.
Mm-hmm.
Okay,
thanks.
Niesh, do you also have?
Yes. No, so I was just wondering about this, I guess it's a related topic that right now you're assuming that basically this stellar mass to halo mass is a universal function and you're trying to constrain it. But of course, it could depend on a lot of other things like on the environment and the history of the halo, all sorts of things. And I mean, so of course, what about that?
Great. So people have checked the dependence on environment and found that it doesn't depend very much on environment. And I think the question about whether it depends on halo assembly history is still an open one. And I'll talk a little bit more about that in the sort of second half of this talk, when I connect sort of individual assembly histories of galaxies and halos together. This is more sort of an ensemble statistics, because I'm not saying anything about how parameters of the halo beyond its mass might affect the stellar mass of the galaxy.
Mm-hmm. Right. But I mean, that's kind of what the MCMC is doing, is trying to, you're minimizing chi-squared for a model in which M star just depends on M halo.
Yes, that's right.
Yeah. So, okay, so you're saying that people have looked at the environmental dependence and they found none, which sounds a bit surprising, doesn't it?
Yeah, so you can, it's not necessarily surprising if you're talking about something like stellar mass.
Mm-hmm.
And we'll talk about why that is a little bit later. But the essential thing is that environment correlates with assembly history, absolutely. And what tends to happen is that, say denser environments where many of the halos formed earlier, except for, say, the most massive one in the environment. So all the sort of less dense halos tend to form earlier because the more massive one cuts off their assembly. They also then assemble their stars earlier. So in other words, when the stars assembled is correlated with the environment, but actually the total amount of stars is somewhat less correlated with environment.
Okay.
Okay, one more from Ghazal, and the rest of you guys take your hands down when you're done.
So in this particular plot, this is at redshift 0, or is it, there is no redshift dependence?
This is 0 to 0.1.
Okay.
All right, I think we're good. Lower your hand, Ghazal, if you're done. Thank you. Carry on.
Great. Okay. So, yeah, so this is a very simple approach if you just have measurements of galaxy number densities. And it's also, I think, as some of the questions we're asking, well, it's sort of like, are you really sure that this is the right answer that you're getting if you have no other way of checking it? And so in the sort of several years since I published, there have been many other sort of checks of this. And so at the time in 2013, it was easy to check at redshift 0 and redshift 1 that there was sort of general agreement with this approach and with other approaches. And then sort of heroic efforts to look at clustering at higher redshifts seem to suggest that we're at least on the right track all the way out to redshift 7, so pretty close to the highest redshift that we were able to look at that time, which is kind of nice. So we made a prediction and then it seemed to hold up with observational tests. And so I mentioned that you can use this as a way to make movies of real galaxies, right? And so this movie of real galaxies that we're making is in some sense nice because it's real galaxies, but in some sense it almost makes us want more because what we're getting here is a movie of how stellar mass changes with time and no other property of the galaxy, right? So these other properties like color, for instance, we have no idea with this approach of knowing whether they're correct or not. At the very least, the stellar mass alone tells us a lot because if we know that a galaxy of this mass lived in the halo at this redshift, and we go slightly earlier and see that a galaxy of a slightly different mass lived in the halo at slightly earlier redshift, we can ask what star formation rate must have occurred in these halos such that you can reproduce this overall growth in stellar mass over time. And of course, you can also take into account mergers in a self-consistent way. And what that lets you do is really reconstruct the star formation history of the universe as a function of the mass of the halo or the galaxy or any other sort of thing that you can look at. So for instance, if we look at the mass of the halo, so here are clusters, here are groups, Milky Ways, and dwarfs, and we look at the star formation history since the Big Bang, we can see that in clusters, in the central galaxies of clusters, most of the star formation happened very early on in a very short time scale. Whereas for Milky Way or dwarf galaxies, it occurred over a much longer time scale. And the cool thing is we can see this over the entire history of the universe, whereas sort of typical ways of measuring the star formation history of a galaxy are most efficient or most credible within the past gigayear and sort of slowly lose accuracy as you go farther and farther back in time. So we can really get a nice picture of sort of all of the history of the star formation in the galaxy with this approach. And if you know the sort of growth history of the halo as well, you can turn this around and say at any point in the history of the universe, if you have a halo of given mass and a redshift or a time, what was the star formation rate in that halo? So this is telling you more about the formation physics. So the difference between this plot and the last one, this was saying for a halo at this mass at redshift 0, what was the star formation rate? Whereas now what I'm doing is saying that a halo of mass, say 10 to the 15 at redshift 0, would have had a lower mass at higher redshifts. And so I'm sort of bending the plot to account for that. What you can see from this is that as you go earlier and earlier in the history of the universe for fixed halo mass, then those fixed halo masses are forming stars faster and faster. And the fun thing is, if you know sort of the halo mass, or from the simulation, you can measure how fast that halo is growing, you can also estimate how quickly are baryons coming into that halo. So if you assume that the cosmic baryon fraction times the dark matter, or the total matter growth rate, is how much gas is coming into that halo, you can actually then calculate what is the efficiency, instantaneous efficiency of galaxies turning incoming baryons into stars, right? So if I have a halo that's mass 10 to the 12 at redshift 2, I can go into simulation and say, how fast are 1012 solar mass halos at redshift 2 growing? Multiply that by the cosmic baryon fraction. And so if I divide the star formation rate that I get here by the incoming gas rate at redshift 2 for a 10 to 12 solar mass halo, I can say what fraction of those incoming baryons are getting turned into stars. And that leads to this very simple picture of gas to stars conversion efficiency, where sort of independent of cosmic time, you have this optimal region around the mass of the Milky Way where sort of half the incoming baryons get turned into stars. As you go much higher or much lower in mass, then you get much lower in both cases in the efficiency of star formation. And so that's kind of telling you that there's something that's preventing gas from turning into stars, and it seems to act in a way that's roughly independent of time. And so this gets back to the earlier question about sort of assembly history affecting star formation. So in other words, if you form your halo earlier, you're forming your stars earlier, but you're not necessarily changing the efficiency of that star formation so much. Great. So are there any questions sort of with this simple picture or the approach so far? I'll just pause before I get to the more complicated stuff in the second half.
So I have a question.
Great.
Even in the optimal case, you're still converting a small fraction of baryons into stars. Why is that?
Great. So you still have feedback. You still have, say, stars forming. You still have black holes that are growing. And so you never expect to get 100% perfect conversion of gas into stars.
Small.
Is the slight change, I have a short question, is the slight change from recent times, low redshifts, where according to this, the optimal halo mass might be around 10 to the 11.5, and then at earlier times, higher redshifts, it looks like more like 10 to the 12. Is that difference statistically significant?
I think it may be statistically significant, but it's not systematically significant. Let's put it that way. So in other words, you have all kinds of systematic uncertainties in converting things like star formation rates and stellar masses from the observations, which are, of course, luminosities and colors, to physical properties. And so, say, a 0.3 Dex offset in star formation rates at higher redshifts would actually balance this out. So you had something more similar happening. Or it could go the other way. So in other words, that trend could become more significant. And we just don't know yet with the current uncertainties about which way that is.
Okay, and James Taylor has a question.
Yeah, I was a bit confused about the axis on this plot and what you were saying about things changing with time. So is this the instantaneous halo mass at that time?
That's correct.
On this plot. Okay, so it's saying every 10 to the 12 solar mass halo converts gas at some rate independent of what redshift it's at.
Yes.
Yeah, okay.
Yeah.
Thanks.
Yeah, and so that's sort of the summary of this picture, is that what really determines this efficiency is mostly the mass of the halo, that is the gravitational potential well depth, as opposed to things like how fast is gas coming in, or what's the background UV luminosity, or how many mergers per unit time are happening, because all of those change dramatically from across this redshift range, whereas the sort of efficiency is not affected so much by that, and it's mostly affected by the mass of the halo, the gravitational potential well depth.
Sorry, then
Yeah,
can I
go
just
ahead.
butt
Go
in
ahead.
with this? a short follow-up question. So the little blip at the bottom left hand of the screen where it's blue.
Yeah, here.
Yeah, so I might then look at that and say, that's telling me that really low mass things have a different efficiency above redshift 2 or 3, which sounds a lot like, you know, the old arguments about reionization and so on. Do you think that's real or believable, that bit of the diagram?
No. What I should say about this region is we have no observed galaxies here. So a 10 to the 10 solar mass halo here is going to host a 10 to the 7 solar mass galaxy. So I should really probably block this area off because we just don't have the observations to constrain anything what's happening here.
Okay, one more from Nayesh, and then we should.
All right. I think you just said something that confused me. You mentioned mass and then you mentioned gravitational potential. But of course, if one is constant, the other is not. So which one are we? I mean, your plot shows mass, but in words you're saying gravitational potential.
Yeah. So actually, to be really specific, it is the halo mass that matters as opposed to the gravitational potential while depth. Although at a given redshift, then they're a fairly close proxy for each other.
Okay, thanks.
Great.
I think that's it.
Great. Right, so I then wanted to talk a little bit about something that's happened more recently. So this was work done in 2013. But now the more recent work that I've been doing is trying to understand galaxy quenching. And so just to define that term, quenching is when a galaxy stops forming stars. And this is something that we've known about for the past sort of 80 or 90 years, is that some galaxies have very different colors than other galaxies, which would indicate that they haven't been forming very many stars recently. So in other words, blue stars like this mean you're star forming, and not having that blue might mean that you've stopped forming stars. And the curious thing is that if you look at a random star in the universe today, most stars, or at least half of stars, are in galaxies that have stopped forming new stars. And if you recall back to the plot that I showed earlier, sort of no more than half the baryons ever have been turned into stars. So you have a lot of gas out there that could be turned into stars, but somehow galaxies are just refusing to do it. And so this has been a puzzle. Why do galaxies stop forming stars, even though there's tons of gas around that they could use to make new stars? And there's sort of a hint in here. For instance, if you look at the star formation rate divided by baryon accretion rate, and that's sort of constant with time, you might guess that halos where the accretion rate is less might have lower star formation rates than halos where the sort of accretion rate is higher. And also looking at this image, if you look in clusters, you find that you have many more galaxies that have stopped forming stars than you have galaxies that are forming stars. And you find many more star-forming galaxies in the field that is isolated, that is far away from dense environments. And so the environment and the assembly history of the galaxy really is telling you something about whether the galaxy is forming stars or not. So satellites, for instance, in clusters, because there's a strong tidal field, the dark matter halos are losing mass. And that's somehow correlated with lack of new star formation. But in the field, it's very rare for a dark matter halo to be losing mass or accreting slowly. And so you have then, for higher dark matter accretion, then a higher chance of being star forming like this. And if you know this, if you know that there's some correlation between the dark matter accretion rate and the star formation, then you can use that to build a better link between the galaxy and the halo. So I'm not saying that there's a causative effect here, I'm just saying that there's a correlation. We can use that correlation to better understand galaxy formation. Okay, so how do we do that? So the universe machine, which is in the title of this talk, is a way of doing that, where we start with the dark matter simulation, as usual, and that tells us things like how does the halo grow over time, how does that merge with other dark matter halos, and then we can guess for how does the star formation rate in the galaxy depend on things like the halo mass and the redshift, which it did before, as well as the growth rate of the halo, so the halo assembly history. And just like for the galaxy formation efficiency earlier in the talk, we don't have to assume anything about feedback. We can just make a guess in this three-dimensional sort of space for what this star formation rate looks like and see how that compares with observations. In other words, any guess for this star formation rate as a function of these three parameters is a way of then putting galaxies into each one of these halos in the simulation. And we can build an entire mock universe from that and ask how close does that look to actually the real universe, all the observations that people have collected, and then iterate. Just try many different guesses for this, create many different universes, hence the name universe machine, and compare those to the real thing. So just show you a movie of what this looks like. So these are Sloan galaxies that have been matched to halos in the Bolshoi-Planck dark matter simulation according to one of the star formation recipes that seem to work in the universe machine. And this is then one of the mock universes that is generated from that. And so the video might be a little bit chunky for you. The main point of this is to show you that you can measure in the same way in this mock universe many things that you could measure in the real universe. So you can measure clustering of galaxies, you can measure lensing of galaxies, you can measure group statistics, you can look for quenching as a function of environments. In other words, anything you can do in Sloan or at higher redshifts, you can also do in this mock universe. You can apply the same systematics, same selection effects, and really use all the information from the real universe self-consistently as a constraint then on what galaxies are doing in this mock universe, right? So you can generate things like positions, redshifts, stellar masses, star formation rates, histories, colors, and so on. So you can combine tons of observations. So things like number densities of galaxies, the quench fraction, how does the star formation of the galaxy depend on its mass? You can look at specific growth rates, cosmic star formation rates, clustering of galaxies, spatial clustering of galaxies, lensing of galaxies, luminosity functions. And so you can combine basically every measurement that people have done of galaxies as a whole across redshifts all into one self-consistent combination. And so it's clearly a lot of work to generate all these universes, but the nice thing is it's a massively parallel thing. So in other words, if you have more processors, you can just generate more universes simultaneously, and you can make use of the largest sort of supercomputers that exist very easily. Okay, so once you do all this, what do you actually learn? So the main thing that we learn from this is what causes galaxies to stop forming stars. And a major hint that comes out is that the star formation in the galaxy, again, depends very strongly on the halo mass. So if we look at the fraction of galaxies that are still forming stars as a function of their host halo mass and the time since the Big Bang, we see that there's sort of down here that almost all galaxies are forming stars. Up here, almost all galaxies have stopped forming stars. And there's some transition region that happens, again, right around the mass of the Milky Way, where you transition from mostly star forming to mostly not star forming up here. And so across most of the history of the universe, there's a fairly sort of sharp transition between star forming and not that occurs as a function of halo mass like this. And something interesting about this is that at fixed halo mass, as you go to earlier and earlier times, you get more and more star formation in galaxies. And this is really robust because in the observations, you see that at fixed stellar mass, at fixed galaxy mass, as you go to higher redshift, more galaxies, a higher fraction of galaxies are star forming. And the stellar mass halo mass relation that I showed you earlier back here was pretty constant with redshift, at least until redshift 4. So in other words, if you look at up to redshift 4, that's this green line here, that's pretty similar to the redshift 0 relation. So until you go to very high redshifts, you don't get much of a change in stellar mass to halo mass, that relation. So in other words, lower quiescent fractions as a function of stellar mass as you go to higher redshift means then lower quiescent fractions as a function of halo mass as you go to higher redshift, like this. And that sort of feature like this is robust and gives us a really nice hint about what could be stopping star formation in these halos. Okay, so just to throw up a couple of models, you can put in lots of different models where it's just cooling rates that give you a quenched galaxies. In other words, as you go to more massive halos, then the gas temperature gets higher and higher, and you can say that, oh, at some point cooling becomes inefficient because of the shape of the cooling curve. And so you can ask, well, is there a fixed, say, real temperature at which quenching should happen, or a constant sort of ratio of cooling time to the age of the universe, or the dynamical time that would cause quenching. And both of those two models would give you a behavior that's different from what we actually observed. In other words, you'd either expect a constant sort of quench fraction with halo mass, or a declining, increasing quench fraction with halo mass for this red model. And you see something different. You see this rising one like this. So to make a long story short, that means that cooling times alone aren't responsible for quenching galaxies, because you wouldn't get this upturn like this. So it has to be something else. For instance, supermassive black hole feedback, or a difference in how gas accretes into galaxies, the geometry of that, which is this Declan-Bernboim model here. So you can already rule out that it's not one popular model for quenching. It must be something else. Okay, so
but the models that, I mean,
yeah.
sorry, Peter, like,
Great.
But the models that you've been exploring with this universe machine, they have certain form, right? So they have that the star formation depends only on like M or M dot or something, right?
Sure.
You haven't like fully explored all possible, I guess, models for this quenching. And so how do you, like, how do you know how robust any of your inferences are?
Okay. Yeah, so that's a completely valid question. So let's say there are other factors that determine quenching. And looking at this, there must be, because halo mass alone is not telling you completely about whether the thing is quenched or not, because in this region, it's not fully quenched or fully star forming. So there must be something else that's going on here. And you also have some sort of correlation with accretion rate, but you also have scatter. So you don't fully know what's causing the thing to quench or not. But that said, you can still say that at fixed halo mass, at least on average, right, that there are fewer quenched halos at fixed mass at higher redshifts. And that conclusion is very robust, because otherwise you would violate the number density constraints. So in other words, you have only a certain number of quenched galaxies at higher redshifts. And if you had a much higher fraction of 10 to 12 solar mass halos that were quenched at this redshift, then you would by far overproduce the number of quiescent galaxies. So in other words, the observations are giving you a very robust constraint, regardless of what kind of model you put in. So in other words, you cannot, just by number density arguments alone, have very many more quenched 10 and 12 solar mass halos without violating those observations.
Go also has a question.
I guess your model has some orphan galaxies. How do you deal with them? I guess it could be critical for modeling low mass galaxies or satellite galaxies, especially.
Great. So we include orphan galaxies, and the constraints for those are driven by matching the clustering like this. So you have sort of joint constraints on, for example, how much satellites can be star forming, from, say, looking at the difference between quenched and star forming galaxies, as well as a cross correlation, which we use as a constraint, but I haven't shown here. And you also then have the overall normalization of the clustering that tells you how many satellites you need. And from the combination of those two, from sort of the red versus blue, the total normalization of the cross correlation, as well as sort of the fraction of star-forming galaxies, how that evolves with redshift, and the number density of galaxies at earlier redshifts when the sort of satellites were first falling in, you can work out that you actually need some extra satellites beyond what the N-body simulations have. So in other words, in the N-body simulations, you're losing satellites a little bit too early through numerical reasons or something else. So we can actually constrain the amount of orphans that you need to match clustering, as well as cross correlations, as well as the evolution of number densities, all self-consistently.
Thank you.
Great. Yeah, so I'm running a little bit close to the end of the hour. So then what I'll just do is I'll skip a few things that I could have talked about and just talk a little bit about satellites too. So we do get many different types of constraints out of the universe machine. One of the ones that I find personally interesting is sort of the range of quenching times for satellites. So there's been a lot of previous work that looks at sort of the average time after a satellite falls in that it quenches, but not that much work that's looked at sort of the distribution of quenching times like this. And what we find is that satellites actually have a huge range in times that they quench. And also something interesting is that satellites are more quenched than sort of isolated or central galaxies, but not by that much. And so that was a surprise to us, given images like this from, say, Bell 1689, where you see tons and tons of quenched galaxies in the center of this cluster. But then what we realized is that these images were misleading because they're taken from a very small region of the actual cluster. So if you look at the actual halo radius of Bell 1689, it's huge compared to some of these images. If you go just a little bit out to, say, 1/10 of the real radius, then you immediately start finding star-forming galaxies, star-forming satellites like this. So the conclusion is that sort of the distance away from the center of the halo matters quite a bit in terms of quenching. So if you get all the way in, you have huge ram pressure forces, you have huge amounts of tidal stripping. It's very easy to quench galaxies. But if you're a satellite that's orbiting around here, then it's a much more gentle environment, relatively speaking. And so it's much harder for you to quench. So rapid quenching in the center, but less rapid in the outskirts like this. Okay. And I'll just throw up a quick plot saying that if you're working on a proposal for James Webb, whenever the next cycle is due, then we also are just coming out with a paper with predictions for how many number counts we'll have as a function of luminosity, stellar mass, and so on. So stay tuned for that. And if you're interested in looking at any of these constraints, actually, you can go to my website and there's a public data release. So you can download all the constraints on things that we derived, like the stellar mass halo mass relationship, star formation histories as a function of environment or anything else, quench fractions, correlation functions, and so on. You can also look at the code. You can run it yourself. You can generate light cones of any area you want. And yeah, so lots of things. So then at the end, I realized that we don't have a lot of time to do the interactive questions. So I'll just then quickly go over some conclusions. So main results. Halo mass seems to be a big determinant in whether things are star forming or not. So over cosmic history, that's mostly what's determined whether things are star forming or not. As you get closer to redshift 0, then things like tidal stripping have started to affect satellites. Then the next thing is that most satellites quench gently like this, so that even though in the center you have tons of quenched things, in the outskirts you have lots of things that are still forming stars like this. Okay, so I wanted to save a couple of minutes at the end to talk about the future. So I hope I convinced you a little bit about the power of combining many different data sets. So in the first sort of half, just by combining the number density of galaxies at different redshifts, I could immediately say something about the halo masses those galaxies lived in without ever making a measurement of halo masses directly. So by combining many different observations, I can get very interesting constraints in galaxy formation. Now in the next 10 years, data will continue to grow uncontrollably. So we'll have LSST, we'll have JWST, we'll have WFIRST, we'll have Euclid, we'll have many new satellites and telescopes built and launched that will just grow enormously the amount of data that we have on galaxies as well as many other things. So it's not just galaxies that benefit from an empirical approach like this, it's also many things that happen inside galaxies. So star formation, gamma ray bursts, black holes. So for instance, I have a student right now who's working on constraining the relationship between black holes and galaxies as a function of redshift, combining measurements of quasar luminosity functions, AGN occupation fractions in galaxies, the black hole bulge mass relation, and so on. And by combining all of these, then we can get a picture into black hole assembly and merger histories throughout the entire universe. So for all of these different topics, I think everyone should look forward to seeing what can empirical models do in the future when we have this enormous amount of data. So it's 9:30 now. I'll end there and say thank you and ask for questions.
You have to clap like this. Virtually or otherwise. Those who have to go, obviously feel free to go, but I think we can hang around a few minutes for questions. If there are any other questions, we had quite a few during the talk.
I have a question.
Yeah, go for it.
So I was sort of waiting for you to speculate on the why question at the end there. You know, convincing point that as you get to higher masses, things get darker, and there's sort of the standard thing that at low masses stuff gets blown out by supernovae, and at high masses, supermassive black holes take over. But one of the things that's pretty clear in massive halos is that, well, first of all, there's a lot of gas. It has a short cooling time, and black holes don't seem to be kicking this stuff out to infinity the way some early models seem to suggest. In fact, it's not clear to me that even at early times when quasars reigned, they're that effective at actually launching matter to infinity.
Yeah.
So logically, it's going to come back. Yet, and it certainly does in the big systems, or it should. So there's still this big gap, in understanding why, even with big black holes in the big systems, they're not forming stars like gangbusters. So, want to take a shot at that? Sorry to put you on the spot without pizza to offer, but
yeah, sure. So I should first give a disclaimer, which is that an empirical model like this, the strength and the weakness is a double-edged sword. The strength and the weakness is that we can't say why something happens. So we can say what the efficiency is. We can't say why it happens. But to answer your question, the nice thing is that knowing what, it's almost like if you went back to your physics class or your astronomy classes, and you got stuck in a problem, but you then were able to look up the answer in the back of the book. And that was often a very helpful guide for how to proceed with the solution. The same thing is happening here, is that we don't know why, but we at least know what the halos are doing. So for instance, if we can say that there is, or the rate of the star forming fraction in halos is very low for massive halos, and the way that this fraction is evolving with redshift says cooling time alone is not responsible, then you have to invoke something else, like black holes, or like sort of the way in which the center is fed by filaments is different at early times to explain this fact. So the sort of speculation that I can give you is that maybe for these massive halos, it's more efficient to get gas into the central black hole than it is to get it in a form that's conducive to star formations. In other words, maybe the gas is going more towards the center than it is in something like a disk, or at least dense enough regions that could form stars. So that's pure speculation. That could be BS, who knows?
Right, but it's still, you still have the M sigma relation, which says that even if it's doing that, it should be for every atom that goes into the black hole, you're going to get 1,000 that form stars. So things are still going to be bright, unless things get screwed up, and they probably do get a little screwed up in the bigger holes, but maybe not that screwed up. I don't know.
Yeah, so it's actually then a little bit useful to show this plot, which I skipped over because I didn't have time to explain what my student was doing. But you can actually then look at, say, what's the typical Eddington ratio, or the growth rate in clusters, and you can ask, is that sufficient to actually blow out the gas? Maybe not to infinity, but at least far enough away to lower the density enough that you're not forming too many stars. And it seems that at least for these massive clusters, it's plausible that you could have enough energy to do that, even though we can't say for sure that this is the mechanism, because that's not what our model can do.
So, but I'm trying to understand. So you're saying that there's enough energy emerging to keep the density low enough that you keep the cooling time low enough that you don't cool it. Is that what you're saying?
So there's enough energy, that is, the black holes need to be growing at a rate to explain, in other words, to be consistent with observations of quasar luminosity functions and sort of the kinetic bubbles in clusters and so on, such that the amount of energy that they're dumping into the gas is sufficient to counteract some of the cooling, or at least most of the cooling that's happening.
Mm-hmm. No, I mean, empirically, we almost certainly know that that's true, but a lot of the models posit that the stuff just gets blown away to infinity. You don't see. But I'll stop and let somebody else ask. Thank you. That was
Yeah,
very nice.
so it's actually worth talking about that a little bit. So if you blow everything away to infinity, that actually takes much more energy than cycling everything in a sort of short loop. So in other words, if you don't blow everything to infinity, but you just like throw it out a little bit so the density gets low enough that it doesn't form stars, you can actually keep that up with a lot less energy than if you are required to blow every atom of gas out to infinity.
Huh, okay. That's interesting. I hadn't appreciated that.
Yeah, and so that's something that's fairly easy to work out with pencil and paper.
Okay, just I have a question. You know, so in your MCMC, when you're like searching over these, you know, like ways of, you know, putting star formation into halos.
Yeah.
You know, can you just like elaborate a bit more on how that's done? Like, you know, so you have some parameters describing the relation between the two?
Yeah, exactly. So to let's go back, which slide am I gonna go for? How about this one? Yeah. So we have parameters that describe this model. And we have parameters to describe sort of nuisance systematics, like offsets between true stellar masses, observed stellar masses, or inconsistencies between star formation rates and stellar masses, things like that, that also go in. And so we end up with a large number of parameters here, something like 45 parameters. And that sounds scary to many people, but in fact, with an empirical model, you want as many parameters as you can that can be constrained by observations. And sort of the reason for that is that more parameters means fewer assumptions from you, the theorist, about what the universe is actually doing. And so you can capture a larger range of what the universe might actually be doing if you have enough observational constraints. And then afterwards—
So is that 45 parameters per redshift or like, or
no,
is that
so that's everything. Yeah, so the shape of this at a single redshift is described by, I think, 10-ish parameters. Depends on whether you count the scatter in there or not, and so on. And each of those 10 parameters has some dependence on redshift. And then you have several parameters to describe things like dust for the colors and systematics for stellar masses and so on. And it's afterwards then, if you see something like this that looks much simpler, then you can say, oh yeah, actually the universe is doing a much simpler thing. We can get stronger constraints if we get rid of some of those parameters. But at least at the first iteration, then you need, or you want, more parameters to be able to describe more flexibly what the universe is actually doing, so you're not sort of under-exploring the space that the real universe might actually live in.
So the follow-on question is, after the fact, would this have been a good enough model? In other words, that there's a universal function that describes the instantaneous efficiency.
Yeah, so that's pretty good, actually. And so many people, after we published this paper, basically had models that were exactly that, and they were pretty decent in fits to a lot of the observations. The jury is still out at high redshifts, what's happening here, whether this is real or not, because we can actually see galaxies here, and we can sort of measure halo number densities. And so this is also the point at which we start to lose many of the colors that are useful for determining stellar masses. And so with James Webb, we might be able to say for better whether this is real or not. You can also see it in this plot here. Sorry, not this one, but one of the later ones, this one, that there's some sign of a higher efficiency at higher redshift, but yeah, we're not sure if that's real or not. If that's real, then you can't fit this with a single functional form that applies at all redshifts.
That's not the instantaneous one, though. That's sort of a...
Yeah, this is the integrated efficiency, but then you can also see this upturn in the instantaneous one, like here. So this little like leg here. If I were to plot this linearly in redshift instead of scrunching redshift 4 to 8 all in this tiny region, then that would be more clear.
Good. I think we should probably wrap up here and thank Peter again in whatever way you find best. So I'll go for the audio one.
Great. Well, thank you so much, everyone, for the great questions. And of course, if you have any more, it's easy to find